Whether it's in offices, labs, hospitals, or data centers, airflow is essential to having them perform well. It's been difficult and expensive to monitor airflow to the level that would enable superior performance. We, at the Center for the Built Environment at UC Berkeley, have developed a novel sensor to measure it. In normal operation, airflow carries the building's heating and cooling energy and the fresh ventilation air throughout the building. During emergency events, it also carries undesirable contaminants such as pathogens or smoke. Knowing about these various flows is important, both for effective normal operation and for being alerted to emergencies. This is a big issue. For example, the amount of energy used to move air for heating, cooling, and providing ventilation totals between 3 and 10% of the total U.S. energy consumption. Currently, airflow in heating, ventilating, and air conditioning is measured by pressure differences in ducts or by the cooling of heated elements in the airflow. These existing technologies have a number of limitations and are generally expensive. Because of this, much of a building's airflow is currently not being measured, which leads to a waste in energy, losses in comfort, and exposure to safety hazards. Together with Chirp Microsystems and the Electrical Engineering and Computer Sciences Department at UC Berkeley, we are developing air sensors for rooms and ducts that are both accurate and low cost. The technology uses a unique invention, tiny ultrasonic transceivers made with high-volume silicon manufacturing techniques that were originally developed by the Berkeley startup Chirp Microsystems to detect distance. The team reconfigured these to measure airflows. Arrays of sensors alternatively send and receive sound impulses to determine the differences in the times of flight along these paths between the sensors. From these, the airflow and its direction can be extracted. The team developed the hardware and the firmware to orchestrate the timing of the signals, to process the data, and to communicate it either locally through USB or over the internet to analyze and display the airflow properties. Different configurations of the anemometers were developed to measuring airflow in both indoor spaces like rooms and within ducts of the air conditioning system itself. The anemometers were meant to run on very low power, so they can run for over a year on a single D-cell-sized lithium-ion battery. This enhanced measurement enables better heating and cooling control and will improve comfort, reduce cost, and enhance safety in a variety of spaces. Data centers can reduce their significant energy costs. Hospitals can more accurately control airborne diseases. Commercial spaces will improve ventilation, reduce energy loss that comes with overcooling, and lower the labor costs of testing and balancing. We hope that these anemometers will improve the quality of life in buildings.